Okay. Today we are discussing the assumptions made in the limit state design. The page 69, clause 38, limit state of collapse, flexure, 38.1, clause assumptions. The design for limit state of collapse in flexure shall be based on the assumptions given below. The following are the assumptions made in the design of limit state. The first one is plane section normal to the axis remain plane after bending. That we have studied in theory of structure. The bending stress assumptions. In the bending stress assumptions, the plane section before bending this remain plane after bending. That means the strain distribution across the depth of the cross section is linear. For this is the cross section. Across this cross section, the distribution of stress is linear. This is linear. So this distribution is linear. That is the first assumption. The plane section remain plane after bending. That means there is no transverse strain in the beam. In the beam bending, take a section. If take a sections, this section is plane before bending. It remain plane after bending. There is no transverse strain in the section. That means it also obeys Hooke's law. After removal of the load, there is no strain, zero strain. That is, this is linear. That is, the strain diagram is linear. It is across the section. And another point is, we have studied the strain at this point is zero and strain at the fiber is maximum. That is another point. The strain at any point is proportional distance from the neutral axis. The strain at any point is distance from the neutral axis. That is, strain at zero, neutral axis is zero, and away from the neutral axis it is gradually increasing. Therefore, it is linear. That is why it is linear. That is the first assumption. The plane section in IS code it is page 69, assumption 38.1 clause A. Plane section normal to the axis remain plane after bending. That is the first assumption. Then second assumption B, the main maximum strain in congate at the outermost compression fiber is taken as 0.0035 in bending. The strain at the congate section, at the congate level, the strain maximum strain will be 0.0035. That is the second assumption. That is laid in the stress diagram. The stress strain curve we have seen in the last class. Maximum strain will be 0.0035. That is the limitation of strain. The congate will be failure at this strain. So we have taken the maximum strain is taken as 0.0035. That is the given in assumption. Assumption is 0.0035, and this is clearly defined the limit state strain of congate in bending compression, beyond which the congate will taken as the reaching the state of collapse. That is, it is very clear that a specific limit of strain in congate does not exceed 0.0035. That is the limit of strain is 0.0035. That's the second assumption. And beyond this, strain 0.0035, the concrete will fail, makes cracks. So, and that also not obeys Hooke's law. That is, after removal of load, it will not come back, and therefore cracks will be existing. So, beyond that point, we will not overload load the structure. So, the maximum limit of strain will be 0.0035. Okay. Then third assumption, the C. The relation between compressive stress distribution in concrete and strain in concrete may be assumed to be rectangular, trapezoid, parabola, or any other shape which results in the prediction of strength in substantial agreement with the result of test. An acceptable stress-strain curve diagram is given in Figure 21. Figure 21 in the same page, IS code is given. For design purpose, the compressive strength of the concrete is the structure shall be assumed to be 0.67 times characteristic. The partial safety factor gamma m is equal to 1.5 shall be applied in addition to this. So this is the stress strain curve, characteristic stress strain curve, and this is the maximum FCK. This characteristic strength is the strength of the cube of size 15 centimeter cube. Isn't this is the strength of the cube of 15 centimeter size. So we are conducting tests in the laboratory by 15 centimeter cube. We get a characteristic strength after 28 days of curing. That compressive strength is termed as characteristic strength. Then characteristic strength is the strength below which the 5% the test results are not found. So this is the characteristic strength, and this characteristic strength for of a cube 50 centimeter size. But the size of the member for our structural member is different. So we are reducing this characteristic strength by a value that is 0.67. That is why this 0.67 is applied. The 0.67 is the reduced characteristic strength due to the difference in the cube size and the structural member. So the IS code is given. The IS code, the stress strain curve figure 21 is given. Look at the figure 21. The first graph, the top line is FCK and the middle line is 0.67. This 0.67 is applied because of the dimension change. This FCK is 15 centimeter cube, but the actual size of the member is different from the 15 centimeter cube. So for a beam, it's 6 meter length or 5 meter length or 3 meter length, and the depth of the member is maybe 60 centimeter and width will be 23 or 30 centimeter. So the difference in this, we are conducting the characteristic strength in laboratory by 15 centimeter cube, and the actual size of the member is 6 meter by 0.6 meter by 0.3 meter. So this difference in the size, so we are reducing the characteristic strength by 0.6. That is 0.6 FCK. And we have already studied the partial safety factor for material strength. That is, for concrete it is 1.5 and steel it is 1.15. That is in clause 36421 in page 68. So again we are reducing this 0.67 divided by a factor of safety. This is for concrete, so it is 1.5. That is 0.67 FCK by 1.5. That is equal to 0.45 FCK. That's the characteristic compressive strength of the concrete. That is the third assumption. The relation between the compressive strength distribution in concrete and the strain in concrete may be assumed. Here it is parabola. The stress diagram is parabola. So it is assumed to be parabola as shown in figure. This is parabola. This stress diagram. So the design purpose where the compressive strength of concrete is parabola, and for the design purpose the compressive strength is equal to 0.6 times the characteristic strength. That is FCK is a characteristic. We are reducing this by 0.667 and then applying partial safety factor 1.5. So this is will be equal to 0.446 FCK. That is we round as 0.45 FCK. So this is the maximum stress in the permission given the congate 0.44. Permissible stress for congate is in the limit state is 0.446 FCK. Then the fourth assumption is the tensile strength of congate is ignored. Congate may sometimes carry small tensile strength as permissible tensile strength, but we are ignored that in the limit design. There is a fourth assumption: tensile strength of the congate is ignored. And the fifth assumption is the stress in reinforcement are derived from representative stress strain curve for the type of steel used. That depends upon the steel used. The stress strain curve is different. For mild steel, there is a significant yield point is shown, but for high yield strength, there is no significant yield point strain can see in the stress strain curve. So depends upon the stress strain curve, it is different. But the typical curve for are given in figure 23. In page 70, the figure 23 gives the typical curves of the stress strain curve of steel. That for design purpose, the partial safety factor gamma m is equal to 1.15 shall be applied. The stress we are conducting, the stress conducted in steel is we are conducting the same type of steel is used, same size of steel is used in the construction also. So there is no need of reduction of the stress for the size factor. So here only the say partial safety factor reduction will be there. For the steel, the partial safety factor material strength is 1.15. So Fy is the characteristic strength, and that divided by 1.15. That's the 0.87 Fy. This is the design strength of the steel. 0.87 Fy, design characteristic strength. And the figure, in figure, you can see that page 70, 23A. 23A shows the deformed cold bar, that is high yield bar. There is no peak yield point. There is no significant yield point. So we are taken as there is no peak yield point. That yesterday we told that the peak point is not shown. Then we are taken as 0.2% of proof stress. 2% of proof stress, that is 0.002. That is in figure 23A. At the x-axis 0.002. That is the 2% proof stress. Corresponding to that parallel line. That line indicates the stress taken as Fy. That is shown in figure Fy. And the second figure 23B, we are reduce that figure into a initially that the proper figure is there is a parabola, so we are eliminating that shape for the calculation, easiest for calculation purpose. So this will be horizontal. This diagram will be horizontal. It's initially the stress is proportional strain, so it is linear. Then and at the yield point or at the 0.2% of proof stress, this stress diagram will be horizontal. That is equal to 0.87. This value is equal to Fy divided by 1.15. That is the partial safety factor 1.15 for steel. So this is 0.87 Fy. Then sixth assumption, the maximum strain in tension reinforcement in section at the failure shall not be less than Fy divided by 1.15 ES plus 0.002. That's the maximum strain. In this figure, you can see that the maximum strain for congate, we are already mentioned the assumption 2.0035, and the maximum, the stress in the steel should not be less than 0.87 Fy. That is, the yielding is more in the steel. So we can take the maximum is the limiting value of the strain is equal to 0.87 Fy by Es plus 0.002. So this is the strain value of steel. So this strain diagram, this is the strain diagram. This upper value is for congate is outermost proper strain is in the congate is 0.0035, and for steel 0.87 Fy by Es plus 0.002, and this is at the neutral axis it is 0. So it's a linear variation. And where Fy is the characteristic strength of steel and Es is the modulus of elasticity of steel. This what is the modulus of elasticity of steel? That is given in figure 23 in page 70. That is Es is equal to 2 into 10 raised to 5 Newton per millimeter square. That is 20,000, 2 lakhs Newton per millimeter square. 2 into 10 raised to 5, 2 lakhs Newton per millimeter square. That's given in figure 23. So the stress strain curve of congate, that is page 69. Page 69, figure 21. The figure 21 shows the stress strain curve of the congate. Here I already told that the topper graph. This graph is the characteristic strength of the congate tube, and we have taken the characteristic strength at 0.002 strain, and the ultimate strain will be, the congate is permitted is 0.0035. So the graph is taken up to this. That is why the plotting only up to this point. Here the limiting value of the strain is 0.0035, and the point at the point up to the point 0.002, the graph will be parabola. This graph will be parabolic shape, and from 0.002 to 0.035, this will be horizontal. So this is the stress strain curve of the congate, and this stress strain curve, that is for already told, for cube size 15 centimeter cube. This characteristic strength of the congate is the size of cube of 15 centimeter after 28 days of curing. And there's difference in the size, member size. We have to reduce the stress, characteristic stress by a value that is equal to 0.67 FCK. 0.67 FCK, and this point FCK, F67 FCK we have plotted. This we get a second graph. That is the corresponding value of this is the FCK value. We are reducing the FCK value by 0.67. So stress strain curve will be this value, this diagram, second diagram. So here the modulus of elasticity of congate, we are taking the modulus of elasticity of congate. The page 16, in page 16, page 16, the second column, EC is equal to modulus of elasticity EC is equal to this 5000 into root FCK. In page 60, that is the Young's modulus of concave EC is equal to 5000 root FCK. So here the Young's modulus is depends upon the FCK value. So the graph will be like this. That is why the graph is shifted to a lower position from the initial position. So the second graph is the Young's modulus is depends upon the FCK value. So this is the FCK value. So correspondingly, we are reducing by 0.67 FCK. So correspondingly, we are reducing a second graph. The second graph, and the design value is design strength, that is given in page 68, already given. The design page 68 cross 3631. The design strength of material FD is given by FD is equal to F by gamma m. Page 68 cross 36 3.1. Materials. The design strength of material FD is given by FD is equal to F by gamma m, where gamma F is equal to characteristic strength of the material and gamma m is the partial safety factor appropriate to the material and the limit state being considered. That is given in second column of the same page 68. Partial safety factor gamma m, second column, that is cross 36.42 gamma m for material strength, that is equal to when the assessing the strength of the structure or the structural member for limiting state of collapse, the value of partial safety factor gamma m should be taken as 1.5 for concave. That is this value divided by 1. The design value is equal to F divided by, this is the F value, F is equal to 0.67 FCK divided by 1.5, that is equal to 0.45 FCK. So the partial safety factor 1.5 is applied to the concave. So we get another curve, third curve, that is given in page 69, figure 21. That is why there are three lines or three graphs in that stress strain curve of the concave. That is FCK. That's on the right side, there is the values are written FCK 0.67 FCK and 0.67 FCK by gamma m. This gamma m is equal to, for concave we are taken as 1.5. So 0.67 divided by 1.5 is 0.446 gamma FCK. This is the stress strain curve for concave. Then stress strain curve for steel. The stress strain curve for steel is given in page 70. In page 70, you can look into the figure for page 70, figure 23A and 23B. The first one is 23A. The 23A, the figure 23A shows the stress strain curve of steel. This is like this. This is Fy for 500 and Fy for 450. Here it is a dotted line. Two dotted lines are shown. That is Fy. Characteristic of the steel 500 Newton per millimeter square. And this is 415. This depends upon the grade of steel. 415 Newton per millimeter square. This two figure is are shown by dotted line. This is the characteristic strength of the steel. Fy for 500 and Fy for 415. Here there is no peak value. There is no peak value and there is no yield point. So we cannot identify the yielding of the steel. There is no significant point. But in mild steel we can see that we know that mild steel, stress strain curve of mild steel is like this. a peak a yield point, then a peak value. This is the stress strain curve of the, this is the upper yield point, this is the lower yield point. So we know this, we can find these values from the graph for the mild steel. So we can take the value corresponding to this. But here there is no yield point value for the high yield strength steels. So therefore we are taken as a strain corresponding to 0.002 or a proof strain of 2%. The strain of 2%. The 2%, that is 2 by 0.2%. 0.2 divided by 100. So this is equal to 0.002. So this is the value, this value. Corresponding to this, we get another parallel. So that is shown in figure 23a. That's the value. This is the Fy for this steel, and this line extended here. This is the Fy for characteristic for 500. So this value is taken for the high yield strength conjugates, and mild steel, we know the stress strain curve. This is the peak upper yield point, lower yield point, ultimate load, and breaking point. So we can identify the yielding. Here there is no yield point. So in IS code, to modify these two graphs, you can use for mild steel or high yield strength. So a modified stress strain curve is shown in the second figure. That is 23b. This is the modified stress strain curve for the steel. So this is the characteristic strength. That is up to the elastic limit. This is stress is proportional strain. After the elastic limit, we are taken as the characteristic curve. The stress strain curve is horizontal. That is Fy. And here we are modifying the Fy value by a factor of safety. In concrete, you can see that there is the size factor we are considered. So it is 0.6 Fy FCK reduces to 0.67 FCK. But here there is the same size. So if it is 10 mm diameter bar, we are using 10 mm diameter bar as steel in concrete. So there is no reduction in the size factor. So there is no need for reduction of the Fy. So only we need the characteristics, the strength by a factor of safety. That is again given page 68. The design values material design strength is Fd is equal to F by gamma m. Gamma m is a partial safety factor that is given in clause 36.421, page 68. That is for steel it is 1.5. So we are taken as 1.5. Fy by 1.5 is equal to 1 by 1.5 is 0.87. That is 0.87 Fy. And here the Young's modulus is 2 lakhs Newton per millimeter square, or 2 into 10 raised to 5 Newton per millimeter square. So it is not depends upon the Fy value. In concrete, there are 3 graphs are shown, separate graphs. The one graph is in concrete. There are 3 graphs. First initially parabola, then horizontal, another a reduced graph and another graph, and this is for reduction of size factor, this is for partial safety factor. Here the FCK EC is equal to 2000 divided 2000 root of FCK. That is you are seen in page 16. Young's modulus is depends upon the FCK value. Here the Young's modulus is constant. For any steel we have taken as 2 into 10 raised to 5 Newton per mm square. So there is no, that is why there is no second line of graph here. So there is no reduction of the Fy. So we are using Fy by divided by a factor of safety 1.5, that is 0.87 Fy. The strain distribution of RCC is as per the assumptions clause 38.1. The plane section remain plane after bending. That means the strain is linearly varying. The strain limit state design, the strain is linear distribution diagram. So it consider a cross section of breadth B and the depth D and the area of steel reinforcement AST. The steel is provided in the congates. This is RCC section, and the neutral axis passing to the centroid of this section. This is neutral axis. The cross section of the, this is the cross section of the beam. And the strain is linearly proportional. That means the strain at the neutral axis is 0 and maximum at the fibers. That we are already studied in the bending stress and shear stress the diagram in theory of structure. The strain diagram is that there we are studied the strain is proportional to this distance from the neutral axis. This is the neutral axis. Neutral axis. The strain is proportional to distance from the neutral axis. This is y. Distance y from the neutral axis. That we are already studied in the theory of structure. So here also the strain is linear distribution, the linear variation. So the 0 at the neutral axis and maximum at the fiber. And the strain is varies at 0 at neutral axis and maximum at the fiber. Then the strain at the neutral axis values are 0 at the fiber, and at the outer fiber for concave, the assumption given in second, the maximum strain is 0.0035, and therefore we can draw the strain diagram. This is the strain variation. The maximum at the concave outer fiber is 0.003, and the strain at a constant stress of 0.67 FCK. You can see that in the figure 21. In the figure 21, the strain up to 0.002 is parabola, then it is horizontal. You can look at the figure 21, page 69. Figure 21, up to strain 0.002 is parabola, and from 0.002 to 0.0035 it is horizontal. That is up to that level. That is after that the strain is, the stress is constant. Stress is constant. That is the strain at a stress of 0.67 FCK. That is 0.002. So this is 0.00. Then strain in steel corresponding to the maximum failure is 0.87 Fy divided by ES plus 0.002. That is given in assumption F, page 69, as second column as F. Assumption: the maximum strain in tension reinforcement in the section at failure shall not be less than Fy divided by 1.15. 1 by 1.15 is 0.87. This is 0.8. Sorry, this is 0.87. Fy divided by ES plus 0.002. This is the maximum strain in the steel. So this is the strain in the steel level. So we can draw the strain variation. That is, this is the variation of strain. It's linear. Maximum at the fiber is congate 0.0035 and steel this 0.08 0.87 Fy divided by ES plus 0.002. So the stress distribution is also linear variation. Is maximum at the fiber and at the neutral axis it is 0. The stress is also 0 at the neutral axis and maximum at the fiber. The neutral axis stress is 0 and the maximum at the fiber of the congate is corresponding to 0.002. That is 0.87 Fy divided by 1.5. 0.67 FCK divided by 1.5. That is 0.446 FCK. And the outer fiber it also again 0.44 FCK. That is constant. That is, you can see the figure 21. Figure 21, page 69. The maximum strain, you can see that 0.0022 strain. 0.002 strain. The stress would be 0.67 FCK divided by gamma m. The 0.67 FCK divided by gamma m is 1.5. So this is 0.67 FCK divided by 1.5. That is 0.446 FCK. And the outer fiber, the maximum is corresponding strain 0.0035. The strain corresponds to 0.0035. The stress is constant. So it again is 0.446. And the strain 0.87 Fy divided by 1.5. That is equal to 0.87 Fy. That is equal to 0.87 Fy. So this is the variation of stress. The variation of stress that is given in the page 69. A stress block parameter that is up to the neutral axis it is stress is 0 and maximum is up to the 0.002 it's parabola, then which is vertical. This portion is given in ISO figure 22 stress block parameter. Okay, thank you.